Hello, welcome to Mr. CFD. This video presents analysis and discussion on the results of this product, which is a paper numerical validation. Actually, the present problem simulates the water flow inside a rectangular computational domain around a dimpled cylindrical body on its inner surface by ANSYS Fluent software. The results of this simulation have been compared and validated with the results in the article Control of Flow Past a Dimpled Circular Cylinder. The velocity vector plot and the contour show flow pattern around a cylinder. We observe three regions. First, stagnation point at the front of the cylinder where velocity is very low, in which it approaches almost zero. And then around the sides, we observe flow acceleration. And finally, a wake region is created behind the cylinder with lower velocities. But now there's a question. How do dimples affect flow pattern? The dimples seem to affect the boundary layer, potentially delaying separation and narrowing the wake region compared to a smooth cylinder. The pressure contours reveal high pressure at the front face of the cylinder or a stagnation point, low pressure regions on the sides where flow accelerates, and a pressure recovery in the wake but not to the level of the upstream pressure. The dimples create local pressure variations on the cylinder surface, which could contribute to drag reduction by influencing the separation point. Let's take a look at turbulent kinetic energy contour. The turbulent kinetic energy contour shows low levels in the free stream, then significant increase in turbulent kinetic energy in the wake region, and also highest levels immediately behind the cylinder. This kind of distribution indicates that the dimples are promoting turbulence in the boundary layer, which is likely helping to energize the flow and delay separation. Here you can see comparing the simulation results drag and lift coefficient to the reference paper. The drag coefficient in the simulation is relatively constant at about 0.83, while the reference shows more fluctuation around a similar mean. The lift coefficient in both cases oscillates around 0, with the simulation showing less amplitude in the oscillation. Finally, we can say the dimples are effectively modifying the boundary layer behavior, likely promoting transition to turbulence earlier than a smooth cylinder would. This early transition helps to delay flow separation, resulting in a narrower wake and reduced form drag. The drag coefficient is lower and more stable than what would be expected for a smooth cylinder at this Reynolds number, indicating the effectiveness of the dimple design. The lift coefficient oscillations are reduced compared to the reference, suggesting that the dimples may also be helping to stabilize the vortex shedding process. These results demonstrate the potential of dimpled surfaces in passive flow control, particularly for drag reduction in bluff body flows. The simulation appears to capture the key physics of the problem and shows good agreement with the reference paper. Hope this video is helpful for you. To benefit from Mr. CFD services including simulation, consultation, and training, visit our website www.mrcfd.com or contact us via info@mrcfd.com.